You can build a data solution that is mathematically flawless. The code runs efficiently, the algorithms converge, and the internal test results are spotless. But the moment it touches a live environment, it shatters. High accuracy in your training data is a baseline requirement for any data science project. It is the cost of entry, not the finish line. A project only succeeds if it survives the unpredictable variables of human behavior, shifting business priorities, and operational friction. Look at this scatter plot mapping technical accuracy against actual adoption. We have a model functioning at 95% accuracy on our x-axis, but because users reject it, adoption drops towards 0 on the y-axis, resulting in a deployment failure. To prevent this, we use performance analysis. This is the systematic evaluation of how well a solution actually achieves its intended objective under live conditions. It requires looking past the code itself to ensure the output aligns specifically with the operating context and business needs of the end user. Bridging the gap between theory and reality requires moving beyond technical metrics. You have to actively evaluate business alignment, user adoption, and qualitative impact. Deploying a model without analyzing its real-world performance leaves you operating in the dark, unable to see the factors that actually determine whether a project survives in the wild. Building an effective evaluation framework starts by dividing your metrics into distinct categories that capture performance from multiple angles. This split-screen layout highlights our first dichotomy. On the left, we track quantitative metrics. This is the objective, numerical data that teams naturally track, like computational efficiency or direct revenue growth. On the right, we track qualitative metrics. These measure the subjective aspects of a deployment, capturing variables like user trust, empathy, and the overall friction of the human experience. Relying entirely on the left side of this screen is insufficient. Mathematical outputs cannot fully capture the complexity of human behavior and perception. The second major metric dichotomy deals with the timeline of your evaluation. This timeline illustrates when data is actually collected. The backward-pointing arrows represent lagging indicators. These measure historical outcomes and final results, showing you exactly what has already happened. The forward-pointing signals are leading indicators. These are proactive measurements, like real-time user engagement rates, that help predict future performance before final results are locked in. Tracking only lagging indicators forces a team into a reactive posture. You only find out a project is failing after the damage is done, eliminating any chance for proactive adjustments. A robust evaluation matrix balances these dichotomies. Prioritizing only objective, historical data creates blind spots that lead directly to failure. The retail chain Target provides a clear case study in how a purely quantitative evaluation process can derail a project. Target invested heavily in predictive analytics to identify subtle customer purchasing patterns, allowing them to deliver highly personalized promotional offers. One specific initiative aimed to predict whether a customer was pregnant based entirely on their shopping behavior, so the store could send targeted coupons. Here we see a visual representation of their data pipeline. The model ingested subtle behavioral shifts, like a customer suddenly purchasing unscented lotions or specific vitamin supplements, and successfully outputs a pregnancy prediction. Technically, this was an immense success. The model demonstrated exceptional predictive accuracy. Yet, the evaluation process was fatally incomplete because the team ignored qualitative factors. They did not evaluate customer comfort, privacy concerns, or the emotional implications of using sensitive personal data for marketing purposes.
Notice this secondary gauge tracking user perception. Target mailed pregnancy-related coupons to a teenage girl, revealing her medical condition to her family before she had shared the news herself. Even a high-functioning model loses its business value if its implementation undermines the very trust it was built to monetize. Technical precision cannot compensate for the erosion of a user base. Google's approach to search optimization offers a direct contrast, showing how behavioral metrics override pure engineering assumptions. Google processes billions of queries every day. At this scale, even microscopic changes to their ranking algorithms have massive impacts. They cannot rely on engineering intuition or theoretical performance indicators. To evaluate proposed changes, they use the controlled experiment, widely known as A/B testing. This schematic visualizes the testing protocol. A single, massive stream of user queries flows in and splits precisely into two paths: version A, running the existing algorithm, and version B, running the modified algorithm. The system evaluates the resulting data based strictly on behavioral leading indicators. Instead of asking which algorithm processed data faster, they track which version generated better click-through rates and longer engagement times. The testing revealed a crucial reality. Minor algorithmic adjustments that appeared technically superior on paper frequently caused unexpected declines in actual user engagement. By tying their evaluation to real user behavior, Google ensures that deployment decisions are backed by practical evidence rather than internal biases. They succeed by allowing real-world quantitative and behavioral metrics to win out over engineering assumptions. A technically improved algorithm does not guarantee a better user experience. To stop relying on assumptions and formalize continuous evaluation, teams use a structured feedback loop called the after-action review, or AAR. This four-quadrant grid represents the AAR framework. It is a systematic process designed to derive actionable learning. The first quadrant asks, what was expected to happen? This establishes your initial intention and baseline metrics before the deployment ever took place. The second quadrant asks, what actually happened? This requires an honest, objective, and bias-free recording of the real-world outcome. The third quadrant asks, why were there differences? Here, you conduct a root cause analysis of the DAP, acknowledging mistakes logically without assigning personal blame. The fourth quadrant asks, what can be improved? This forces you to translate the reflection into highly specific, actionable strategies for your next iteration. This methodology strips emotion from the process. It prevents teams from falling back on surface-level excuses when their operational metrics fail to align with their technical tests. The after-action review transforms passive failure into a systematic engineering autopsy, making continuous learning a formal operational procedure. The work of a data professional does not end at the command line. A theoretical model only creates value when it proves itself in practice. Let's return to our original scatterplot. By integrating qualitative data, leading indicators, and formal reviews, the data point begins to shift upward on our y-axis. These frameworks don't offer a magic fix, but they provide the visibility needed to realign technical outputs with human and business requirements. Performance analysis is an ongoing cycle, not a one-time checklist you complete prior to launch. Organizational goals pivot, new data patterns emerge, and user behavior shift. Your evaluation metrics must continually adapt alongside them to remain relevant. If you cannot measure a solution in its actual operating context, you cannot improve it. Rigorous, multidimensional evaluation is the only true measure of deployment success.